Okay, so today we'll start discussing about the joints that you will need to design for your project. Now, for the project, you will have to design the following joints. The beam to column joint in a moment resisting frame. You can design either this, it doesn't matter, just as typology. This is a moment resisting connection. You will have to design also the beam to beam connection, the secondary beam to main beam connection. Okay, this is a shear resistant joint. Next, you'll have to design a continuity connection for the column wherever you want in axial force. Okay. On the next frame, you'll have to design a brace connection here. Here will depend the actual detailing of the connection function of your bracing system. So if you have X braces or V braces, this should be pinned. In case of the current model using eccentrically braced frame, so links, this should be rigid. So the connection would be a bit different. For those who have links, here should be also another connection, and regarding the beam here, it will be a shear resistant connection. The last one will be a base connection. The project, the drawn part, you will have, for the drawn part, you will have to draw a general assembly drawing for the moment resisting frame, transversal and longitudinal braced frame. So, if you choose to have a drawing for this column, you should think also of the connection in this direction and also perpendicular. Okay, so do not neglect all the necessary elements that will be connected to what you want to do. Now, going back to this connection, we will start with a beam to beam connection, a shear resistant one. Let's take this beam. It doesn't matter for you for this example here. In your project, you will have to check the beam that's most stressed and take the maximum shear force. Okay, being a double pinned element, you'll have bending moment in the span and shear resistance in the support. Now, the detailing you may use, for example, SteelCON, and I will detail it briefly, or in principle you follow Eurocode 3 part 1.8. For this example, we will go with a class A, category A joint, which works in shear. You can use also class B and C for different limit states, which are with pre-tensioning, so to prevent unfastening of the nut, and the resistances are detailed here, FVRD and FBRD. Now, I've already taken an example of a main beam IP 400, a secondary beam IP 300, and I already made the necessary cuts. These cuts on vertical and horizontal, both up and down, are due to technological reasons and also due to how elements are behaving when subjected to loads. So if we do not cut here and here, we cannot basically connect these two elements, because if we check from above, okay, and if I extrude, I cannot physically lift the secondary beam and connect it here and here. That's one thing, and I need to have some distance such that this corner will not hit the web of the main beam. Okay, these are the distances that I've implemented. I also needed to lift the secondary beam to the same level of the main beam, given the fact that I have a slab which is at that level. Okay, so that's why I implemented this distance. Now you can check this in 3D how it looks. Okay, also side view and front view. Then I went to the second tab, which is for the cleats or plates and for the bolts. Now I've started with two M16 10.9 class, okay, and I've implemented 3 bolt rows and 1 column. For this example, I've selected just one cleat, okay, of 80 millimeters width, detailed here, okay, and 12 millimeters thickness. You should choose more or less the same thickness of the secondary beam's web, and function of the length, you will have some conditions which are, let's say, stability ones that prevent the lateral torsion of the main beam or the secondary beam. That's why you may have to increase a bit the length. Now, you should also take care of the weld thickness, let's say 0.7 multiplied with 12, this is 8.4, let's go with 8, okay. Now, here are the minimum distances that should be taken accordingly to the diameter. I will apply the changes and then I will hit here solve and here analysis results, and I will check here the results. Now here I have a multitude of values. For the beam resistance, I have in all the resistances for all stresses, and I have the strength of beam in rupture and bearing. So being the fact that the secondary beam in this section, okay, so just the secondary beam, will have a resistance in shear and a resistance in axial force. Now, applied rupture force, it's 60. 60 I've taken from the shear force diagram. Again, you should take the maximum one, okay? And I've implemented here in the loading case. So here, load cases with negative, because I have here the corresponding positive axis. Now, if I go back on the results, just 1 second. Okay. I need to check the ratio. So basically, I have 3 components: the shear resistance of the bolts, the bearing resistance of the beam web or of the cleat or of the plate, whatever I choose to use, and the resistance in net area. Can be the resistance in net area in the plate or the resistance in net area of the beam. It depends. And these results are presented here. So for the fin plate or the angle, I have strength in shear, it's this one, okay? In bending moment, we do not discuss on a very simple connection if you want to decompose due to eccentricity and so on and so forth. So you should take into consideration this. Bolt resistance in shear, it's this one, it's per bolt, and I have just one shear plane, so that's why I have the resistance so small. And I need to check also the net area. This is this one, okay, in VZ, in shear, okay. And for the cleating bearing, it's this one. Now, if I do not satisfy the ratio, so if I have here greater than 1, and here it shows that I have secondary beam bolts in combined axial force and shear, I have over 1, then I need to check the minimum component and increase accordingly. Let's say I need to increase to M20, okay, apply, and I have here another component, and this ratio is different, okay. If I go back and I want to see the report, I go to File, Print Out Content Selection, and here I go to Short or Normal. Please don't choose Full, because you'll have also the theoretical part, so on and so forth. And after solving and checking the results, you may go to File, Print, PDF, and here you will have the report, okay? And here are the resistances, what's applied, what's not. You see also the geometrical properties and so on and so forth. Now, this is how you check, very simple, a beam-to-beam connection to shear force. The second one may be a, let's say, continuity connection for a column, okay? Let's highlight for this frame. Let's choose, for example, this one, and not in shear but in axial force. But let's discuss about the location. Where do you think the location for the continuity connection for a column should be?
In the area of the smallest bending moment.
Okay, here in this connection, for this combination, sorry, here I have M3 and here I have axial force, okay, left and right. Here it's because I do not have wind assigned on the structure. If I have wind, I have also some kind of bending moment. If I choose from dissipative, let's say no displacement, this one, okay, on X, bending moment, okay. Look, I have here a bending moment of minimum 90 kilonewton meters and maximum 94. Okay, so I will take the absolute value, the maximum absolute value, which is 94, and in another combination I have the axial force of 980. Do not mix them, so you have to take the axial force from this combination and also the bending moment from this one. You see I have 0. This is both for the column design and for the connection design. And when you check from the other combination, take the stresses accordingly. Now, the thing is, you should go in the section where you have minimum bending moment. What's the maximum length of an element that can be transported on site?
30 meters.
12-30 meters, yes, without taking into consideration special transport, okay? So, given the fact that I have a 4-meter story height, where could I think of placing that continuity connection for a column?
10 meters.
At 10 meters would be, let's say, a good option. So I have here 4, 8, somewhere here, okay? Somewhere in the middle, let's consider here, look, at about 2 meters from here, or 10 from the ground, I have almost no bending moment. There I should place the continuity connection, because I have only the axial force. Axial force from this combination is 300, from fundamental it's 900, and from non-dissipative again 300, and combined it should be more or less 300. Now, given all this, ideally, you should design to plastic capacity of the section. So to end plastic of the column section, ideally, because you want that continuity connection to be stronger than the capacity of the column, yes? That's how you consider an element that's continuous on height. To do that, in some cases might be difficult, okay? Even for this project, if it's too much, you can consider designing to the maximum from fundamental combinations, or persistent design combinations, and situation and transient. So either dissipative, non-dissipative, and fundamental with maximum axial force. okay, if you cannot design it to plastic capacity of the section. And for that you basically go here to just to save this, I want to see the modeler. Okay. To miscellaneous connection, and this might be one, okay? Now, here we have a 3D view. Here it's detailed the connection on one part, top, side and front. Okay, so here we have a HEA 450. Let's choose another section a bit smaller. Let's say HE 400B. Okay, HEB 400. Okay, now we have this section. You have the steel quality. You can have the type of the connection, either mixed, either welded, either bolted. Let's choose bolted because we have the same detail. Okay, and you should choose here the gap. There should be a gap between the section. So actually the sections are not resting one on the other, there is a gap. Okay, and when you tighten the bolts, the shank should not be in contact with the hole. Okay, there should be, the stress should be transferred by that friction. So that's how the element should stay. Okay, now here you have to satisfy the connection, so the plates and the bolts should be designed ideally to end plastic. Now, how you do that? I suggest having at least the same width. So here it's 200, 300, I think. Yes. Function of the capacity. You may even add plates here if you need them, but take care how you can add them technologically. Also, take into consideration the net area. For example, if you detail the bolts in the same line, even technologically you might not be able to fasten them. So you need that to take into consideration. Otherwise you can put them staggered, and you can use bolts with a diameter which is a bit larger. Let's say M20, up and down, 10.9, 10.9. Let's say 4 board rows, and I can see that from above, and I should have them symmetrically. Just a second. Uh, 60, 70. Okay, this prevents, it's stupid because it prevents the, okay, width of web plate, this is this one. Okay, this should be smaller. Just 1 second. Width 300. Okay, and I need to adjust this one. But from the top I have everything symmetrical. Okay, this is good. And from the front view I need to have this So I want to have this a bit to the right. Okay, something like this. This I can play it a bit. Okay, I remove that error. Okay, I need to spread them just symmetrically. Let's say this here, 65. Now they are symmetrical. Okay, this it's a bit too, it's too close. Just 1 second. Something like this. Okay. Now, apply, solve. And here I do not have any stress implemented, so I have applied stress 0 bending moment, 0 shear, 0 axial force, but I want to check the capacity. So I have the resistance in shear of 1 bolt because I have several planes on the flange plate. So here I have one shear plane. I have 150 for the shear resistance. I have for the bearing 156. For the bolts in shear I have 1800. For the plate in tension I have almost 1000. This is here. Now I have here bolts resistance in shear on the web plate. It's this one. Okay. Again I have bearing and shear resistance, and these are only capacities. If I put, let's say, minus 1000, now I have the minimum component, the ratio 0.46, web plate, bolts in shear. Basically the bolts here will be subjected almost to 50%. Now if I check if I have not made a mistake, it's almost 7,000 kilonewtons. So it's 198 multiplied with 100. This is in millimeters squared multiplied with 355. Yield limit divided by 1000. It's 7,000 the capacity. So I've implemented 1000 and I have 50%. If I will put 2000, I get 100%. That's why I'm telling you it's pretty difficult to go to that value. Okay. Now, please check what's the maximum value in terms of axial force and so on and so forth from dissipative, non-dissipative, persistent design situation. And if you cannot reach that value, at least reach these ones because these are important. Okay. Have a partial safety factor, let's say of 2, let's say, and you should be in a good situation. Okay, so here if I will put 2000, but I also need to check the shear force and bending moment. Okay, I'm at 92%. I can go even to with more bolts because here I have just 12. Okay, and here I have again 12. I can decrease a bit the diameter, increase the number of bolts, and play also with this, even with the bolt diameter. If you need again thickness of the plates, you can do that, but here it's the bolts. Okay, that's why I'm telling you need to understand what's the minimum component, because the minimum component, if it will be the plate, if you increase the bolts, it won't have any effect. That's how you check this. Okay. Any questions regarding these two joints? Okay, the next one will be a bending resistance joint, a beam to column connection. And according to P100, not this one, there are some things you need to take into consideration, which are partial safety factors, okay? One second. Just 1 second. Okay, so the resistance in bending should be greater than 1.1 multiplied with the overstrength factor, function of the yield limit, the steel grade, and according to the actual resistance of the element. Now, this would be something like 1.1 multiplied with 1.25 multiplied with the bending resistance. Function of the typology, you will need to take into consideration the plastic hinge location. Now, for the moment resisting connection, choose this one, okay? And here are the parameters, okay? I will choose a T connection, so a marginal column, let's say an HEB 400, an IPE 450, okay? Steel grade S2355, okay? The downside of this software is that you cannot have different steel grades for different elements, yes? Now, according to the 3D view, something is wrong because the end plate is not as long as it should. Okay, I will go to this one and implement a bit, let's say 600, okay? Now it's more or less okay. If we go to front view, we see that for this extended end plate connection, which is unstiffened, I can introduce more borders. I suggest checking this document, okay, this is in Romanian, but you have also in English, volume with information from Equal Joints Plus for seismically qualified joints. And you have 4 typologies, just 1 second, and are these ones. Unstiffened end plate connection, stiffened end plate connection, both extended. This is with haunches and this is with dogma. Function of your zone, your PG, you can choose one of these 3. If you do not have stresses which are so large, you can choose this. Might be difficult, so I suggest sticking with this or this. However, for this case, you cannot perform in SteelCON because you do not have that triangular stiffness. Now, if you choose this, you need to amplify the capacity due to shifting the position of the plastic joint with this haunch. What's interesting in this document is that you have some sort of pre-dimensioning sizes that you can take. So, for example, you see here that for a beam size of approximately 450, you should take M30 as bolt diameter, 6 bolt rows, and the end plate about the thickness of the diameter, and the angle of the haunch, so on and so forth. There are some considerations to which you can apply this typology, and we can choose the same. Okay, let's go to, I think let's M30. This should be a bit bigger. Let's go M27. Group 10.9. Okay, this should be 600 and I should have 40. Okay, 90. The width should be larger. The width is here. 150. I need to have even 120. It's okay. 150. Okay, more or less it's symmetrical, like very quickly detailing it. Okay, I have the same distance here. This here should be the same distance. Okay, just 1 second. Because you should have it symmetrical. Okay. More or less. I think it's okay. This is 80. Now it's symmetrical. Okay, perfect. So I have this distance equal with this distance. This is a bit bigger. These are symmetrical. Now the joint looks like this. It should be updated, but it's not updated. Okay, let's apply. The 3D is not consistent, but the 2D is okay. So I need to increase the resistance of the weld. Why? Here I have the thickness way too bigger for the throat that I consider. Let's say a 6 and a 8. 10 and 7. Okay. Good. So the weld resistance is okay. Now this is unstiffened, and if you check from the side, you see that the web panel is quite flexible and I have some bolts. Let's check the resistance. Here you have stiffness results and strength results. For the strength, for the bending, you have here the result. For the shear, here the result. Now, the plastic capacity of the beam is the following. I've chosen 400 or 450, 450. Okay. Plastic modulus. (600 kilonewtons). 600 kilonewtons. Okay. Now 600 kilonewtons, and I have a resistance of 450. It's okay or not?
Wasn't it like 6,000?
It's 1702 multiplied with 10 to the power 3, and this is divided to 10 to the power 6. So it's 1 second. I forgot to multiply with 355. So 1702 from the catalog multiplied with 355 multiplied with 10 to the power 3 in millimeters, because I have here in catalog. Okay, multiply with 10 to the power 3. And I have this value. This I need to divide to 10 to the 6, because it's in kilonewton meters, the bending resistance. Okay, 10, 100, 1000, and another 3. 1, 2, 3. 604 kilonewton meters. Okay. Now I have 455. It's okay or not?
It's okay because it might be stronger than the capacity of the column in order to resist.
Again, it's
The-
not okay or okay?
It's not okay because it's smaller than the capacity of the
It's even smaller than the capacity of the beam.
beam. Yes.
Okay, so if you look here and if you look to the to this typology, you see that there are some stiffness here. If we go here to the and we haven't even discussed about stiffness, but if we discuss about strength, you see here how the bolt rolls are loaded, and only 3 bolt rolls are loaded. How they are loaded? These are the minimum components, and you can see them here. So for bolt roll 1, this one, the minimum component is end plate in bending, which is this resistance, and it's this one. Okay. For the second bolt row, it's column web in tension, so here, and I have also the failure mode. For the third bolt row, it's this one. Now, to increase this, if I would have taken M2024, now, if I want to increase the capacity, I need to take into consideration these minimum components, because if the minimum component is something about the column, if I increase the bolt or the end plate, will it drastically improve the capacity? No, that's why I need to understand this. Because I have also the column web panel in shear, which is a component that reduces basically the total resistance, and also some other elements. I can take into consideration that. Also, I can put that stiffness here to increase a bit the stiffness of this joint and also the resistance. These are called stiffness or continuity plates. Usually they are the same as the remaining width and also the thickness. It's more or less the thickness of the flanges of the beam. Okay, and okay, let's increase a bit also the length of the beam. Okay, let's say 6 meters. Now I have 559, a drastic improvement. Okay, and if I check here, I can see that my bolt rolls are loaded even more due to some components. Okay, which is very good. However, I need to increase. How much? Actually, not to 600, but to 600 multiplied with 1.1 multiplied with 1.25. Okay, good. Now, what else can I do? I can check now the minimum component. The minimum component for the bolt row is end plating bending for bolt row. For the second one, end plating bending. For the third one, beam web column web panel issue. Okay, from the two bolt rows, what can I increase to improve the capacity of the connection? End plate in bend. Okay, if I increase the end plate, it's 20. Let's go to 25. Okay, or 28, 7, how much we have. Do not go over the diameter of the bolt. Okay, I have from 559 582. I did not reach the required. Okay, why? If I go to 27, let's say maximum, I have 530, so it decreased because other component was critical. Okay, so I can go only to 25. Conclusion: at some point, even if you add, because if I increase the bolt diameter, it won't help drastically. Let's increase, okay, to M30. Neglect the resistance. I have only 600 from 580. It's not very big. I can go higher, okay? More or less, this is the maximum capacity of this type of joint. So it's a at limit resistance equal with the resistance of the beam, but you cannot go with overstrength. In order to go with overstrength, you need other elements. Other elements might be in another typology. Other typology might be using either this and either this. 1 minute to discuss about the stiffness, and then we'll discuss how to improve that joint. These are more or less partial strength, partial rigid, okay, in terms of stiffness. These are full strength or equal strength, and I think they are rigid and semi-rigid. Function of how you detail this. This can be full strength, full rigid. Okay, these are the stiffness of the three. Now, what do you remember in terms of stiffness? Here I will plot the M5 diagram. I have the stiffness written here. What type of joint function of this stiffness is what I have detailed here. Remember about zone 1, zone 2, and zone 3. If you have the curve in zone 1, you have a rigid joint. If you have in zone 2, you have a partial rigid joint. And in zone 3, it's formally pinned. Okay? And here are basically the limits, how they are computed. Now, mine is semi-rigid. I've considered rigid joints, so I need to increase the stiffness. Okay, I've told you this is about the maximum capacity of this type of joint, so I need to implement a haunch. Okay, but take into consideration the frame. For example, I've implemented the length here, but I did not consider if it's a braced or unbraced frame. My frame in this direction, it's moment resistant frame, so unbraced. So my limits are okay. If you design on the other direction, you need to implement braced. So that limits like this will be like this or like that. And it's a big difference how they are the limits. Okay. Now here I will implement a haunch. Okay. Let's say a 150 by 150, 180. 180 by 180. I will go with full strength stiffener. Please implement the stiffener because otherwise it won't help you. Okay, now this area is much more rigid and I need to check also the geometry of the bolts and the end plate. So I go with, let's say, 700, 750, 780. Here I will go with 200, 150, 150. And I have here 70, 20 millimeters more, 800, okay, and I want this to be 45, so I need 160, okay. This, it's not symmetrical compared to the asking an extended end plate connection, okay. However, here I have a warning regarding the distance. You should check that this can be fastened, okay. So this should be a bit higher. Now let's neglect for this example this. Apply, check. Look how much I have. 837. Okay. However, I needed to have 830. Okay. 830 for that connection, because for this one the haunch here will reduce the clear length and will increase the needed capacity. How you can compute that? According to this document, here is detailed, okay? So you have N plastic, which is taking into account 1.1 and 1.25, 35, how much you have from overstand, and also the shear force due to translation of that haunch. So SH is the length of the haunch, and you need to compute the shear force that can develop due to clear length, same as in concrete design, more or less, yes? Because you have twice the bending capacity divided by clear length plus the gravitational load from that combination, okay? And here you will get that. Let's say for this we have shear 83, but this should be smaller because this is also with seismic, let's say about 40, and I have 4 meters and something. So I have 600 to multiply with 600, yes, kilonewton meters divided by 4 meters. It's more or less 4.2, 4.5. The clear distance between the columns, let's say 4.5. It's 260 plus another 40, it's about 300. Maybe less, maybe 200, okay? But that 600 or 600 plus 300, it's 900. So you see, this is very quickly, that's just an example. You see how much you need to have here. So you may play a bit with the end plate. Let's say if you have that as minimum, okay, and I have here 846, I still need to find an additional 50 kilonewton meters. But let's check the stiffness. It's semi-rigid. Okay, I can improve the stiffness by implementing also supplementary web plates here, okay? And now I'm at the limit. If I improve that area, let's say 10, I'm almost in zone 1, I can consider zone 1, okay? So now I have also here, look, I have almost 900, so I'm at the limit, what I needed. almost, okay, almost. And I have also the joint almost still. Okay, so it's not that quickly to design this type of joint, and this is very simplified what I showed you here, because you should check on bolt holes, control the failure mode, so on and so forth. In some cases, maybe even the sections are not properly assigned. So in some cases, you might be in the situation of taking another column section because that column might be too weak, because you have large spans, for example, and so on and so forth. Okay, that's due to that type of connection. Just 1 second. I can also provide this, so we discuss about these three. The last will be the base connection and also that brace connection, but the brace connection is similar with the beam to beam connection, but it's in another term. Okay, now we will discuss about the base connection for our columns. Okay, these are few considerations to consider when we want to design the base connection, and we will do that with SteelCON. So we'll consider a base connection, which is this one, miscellaneous connection. Okay, and we have this block. Now when you will detail for the project, please consider this type of connection, yes, with a reinforced concrete and a pillow. Now for this current project we will not perform the check for the foundation, so to check the reinforcement, so on and so forth. We will just consider some minimal dimensions for the block and for the pillow, such that it doesn't fail in shear in this section. These are provided here, the angles and the ratios, which will also be available on your campus. Now the column, as it was designed, it was from two combinations: from persistent design situation, which is fundamental, with maximum axial force, corresponding bending moment and corresponding shear force, and from transient design situation, meaning seismic, either non-dissipative, either dissipative, function of the structural type. We have maximum bending moment and corresponding axial force and shear force. Now let's take just a example of a column, and let's consider this. So first I want to save it just to make sure that I do not lose this. I can save it here. Base. Okay, let's consider an HEB 400. Please introduce the column length. I will leave this to 4 meters. Okay, the steel quality I'll go with S355. Concrete, let's consider at least C25 by 30. Here you should pay attention to these options. How should the column be oriented for the moment resisting frame? So the moment resisting frame should be on vertical direction or on horizontal direction? On vertical direction. So the flanges to resist to bending moment. Okay. And here it's written the following: the frame is braced and non-sway in columns strong axis, is braced and sway in columns weak axis. So which one of the two I should pick? So is braced here, yes. So in strong axis I should pick this. Why is this important? As for the moment resisting connections, you have the two limits for which you consider the joint to be classified function of the stiffness, meaning rigid, semi-rigid and pinned. And that limits can be like this or like that, okay, 3 times smaller. What type of connection we want to design for our project? Rigid, semi-rigid or pinned? Rigid, correctly. Therefore, we should take care that if the limits are 3 times smaller or larger, will impact how we consider our connection, yes? Because you may be rigid, but in fact it's semi-rigid, okay? So this is very important. Now, we do not consider the reinforcement check, okay? We may just alter this. These are the dimensions for the block, vertical, horizontal, so on and so forth. Now, we may go to this tab, which is for the bolts. Let's consider hooks, okay? And firstly, just have not 4 rows, but 2 rows, 2 columns, which are this one, okay? Like that. And we should have the distances in between larger, like something like this, okay? Now, here I do not have any stiffness, yes? I can implement the capacity design for the stiffness that you should do when you use the stiffness, and here you should employ, if you use J hooks, for example, you can use a group like this, okay? So M30 maybe 5, 6, okay? Apply, and let's check the results. I will go to stiffness and to strength. Now, for the stiffness, I have here M5 diagram, and it's no limit, it's always rigid. But this is very strange because there should be the limits employed. Okay, here you should introduce the dimension for D, which is for this, okay, for the diameter. It's actually a rigid, a minimum value that you will get as an error if you do not implement that. Because I do not have any stresses. Here, okay, you should have more or center the hooks, okay? Let's put, for example, for axial force, meaning like this, let's say minus 2000 and minus 300, okay? You may even have biaxial bending. Okay, apply, solve. So, here the welds did not resist, but it's very strange that I do not have that limit. So, here the welds, I need to go with, let's say something like this. This is not rigid because this is pinned, but it's very strange. I'm not sure if this is a bug or not, but now we have in zone 2, so it's a semi-rigid connection, and this result is correct, because if you look from top you see that it's quite flexible, yes, because we do not have stiffness, and this should be as expected. Now, in terms of resistance, I have here the ratio, okay, in axial force and biaxial bending, it's uniaxial, it's 84%, okay. If I go to a higher value for this, now it's okay, because my ratio, it's this one, so this is what's expected, not the welds to be the minimum component, but actually the connection as a whole, okay. So for major bending I have a 38% utilization factor, and for axial force 46, and the combined effect it's 84, okay. So this is correct, but I have performed just one check, okay. I need to check also for maximum bending moment, and for maximum bending moment here are actually some values, okay. So if I put 700 kilonewtons, I'm pretty sure it won't resist, okay. So if I put here not 300 but 450, not even 700, yes, you see I have 1.1, okay, 1.11. Now the first thing is to increase the capacity, and also to have the connection rigid, not semi-rigid. Now, to do this, we should implement stiffness. You should go from 2 rows to columns to 2 rows to columns with stiffness, okay, like that. We should increase the height to 750, let's say 550, and the distance 400, even more, 450, something like that. You may have some warnings here that you need to deal with, so try to go with minimum distances here, okay, and also here. This should be more or less okay. Now if you want, you can implement also on the weak axis stiffness, okay. I will go with 50 millimeters, more or less, like 150, also here 150, but I increase more and decrease a bit the welding, the weld thickness, okay. This is clearly something regarding the stiffener, so I need to increase the height at least, so this is an L. Let's go with 200. And you have here a warning that it's too slender, okay. And now you see that I have 0.72 major moment stiffness in bending, so actually the minimum component are the stiffness. But if I go to this, I still need more, okay. I can go for the stiffness with some additional stiffness or to increase the height, but you will see that it won't severely change, okay. See, it's still semi-rigid. You can even implement this if you do not need bolt there, okay. However, you can consider something like that, okay, 9 bolts. When you will do that, the stiffness increased, and you can increase it a bit also with the that was the dimension I was telling you about in the beginning. Let's say 1600, 1600. 275, okay. We still need to go higher. Okay, but more or less this is a very good option in terms of either adding bolts, either considering stiffness a bit higher. If I want, I can increase a bit the dimensions in plane, and this will help me a lot. For example, this and this 600, okay, and I will put this to 500, 480, and vertical something like that. Now I have the surface larger, so this should be in 8 to this. Okay, it helped a bit, so I still need a bit of increase in the direction such that it's rigid. So more or less this is how you should play to have the joint properly designed. Okay, and here please put your dimensions more or less, so do not focus a lot on this. The focus is on the connection. The thing is that you will see if you increase the end plate, for example, now it's 30 millimeters, okay? If I increase it to 35, it actually increased that. Why? Because when I increased the thickness of the end plate, it changed the type of end plate in terms of location, what we discussed previously, what type, which is on one direction, on two, so on and so forth, okay? And the thickness changes that geometrical parameter, which in fact increases the stress on the stiffness, so that's why it increased this. So actually it's unfavorable to increase the end plate in some cases, which is this one. Also the stiffness, to increase them a lot or make them too thick, so on and so forth. So more or less these are some guidelines that you may consider when designing your joints. Okay, it increased a bit the stiffness also. Questions?